Next, we consider the second order optimality conditions for problems with both inequality and equality constraints. So, and as before, the problem that we'll consider will be given by minimizing f of x, subject to m equality constraints h of x is equal to 0, and then p inequality constraints g of x is less than or equal to 0. And as before, we'll use the notation for the indices corresponding to the active constraints at x star, which is given by I of x star. So this is the set of indices for the constraints that are active at the point x star. The Lagrangian in this case is given by L of x lambda mu, which is f of x plus sum of lambda i's h i's, and then plus sum of mu j's g j's of x. And the Hessian of the Lagrangian will be this expression here. So this part is the same as for problems with equality constraints only, and this part corresponds to the Karush-Kuhn-Tucker multipliers times the Hessians of g j's of x. So this corresponds to the inequality constraints, right? When we talk about local optimality conditions, inequality constraints are actually irrelevant if they're not active. So if an inequality constraint is satisfied but it is not active, then this inequality constraint has no impact on the local optimality properties for the point. And we only need to focus on the active constraints in this case. Therefore, the tangent space that we define here is as follows. So T of x star will be given by the set of y's such that essentially the Jacobian of the functions corresponding to only active constraints times y is equal to 0. For the equality constraint part, we still have the gradient of h i's of x star transpose times y is equal to 0. And then for the active inequality constraints, we have the same condition. So essentially, we treat them just like the equality constraints because this is what they essentially are for the point x star. So with this definition of Tx star, we are ready to formulate the second order necessary condition for our problem. The second order necessary condition is given by the following. So it's pretty much the same as for the case with equality constraints only. So if a regular point x star is a local minimizer, then first the KKT conditions are satisfied with some lambda in Rm and non-negative mu in Rp. And then second, for any y in the tangent space T of x star, we have the following inequality hold. Y transpose times the Hessian of the Lagrangian times y is greater than or equal to 0. All right, so pretty much the same condition, is just we add the active inequality constraints in the mix. Everything else is the same as we just discussed for the case with equality constraints only.
But there's not all.
Then for the second order sufficient conditions, you would probably expect a greater than 0 sign here, right? And if for any y in T of x star, this product is greater than 0, then x star is a strict local minimizer. However, in this case, this logic doesn't work directly, okay? So we need to actually require this inequality over a wider set than T of x star, okay? We need to have a stronger condition, so just requiring positive definiteness over T of x star is not sufficient. But if we somewhat expand this space T of x star here and require that this inequality holds over that wider set, then we will obtain the second order sufficient condition for this case. All right, so let's discuss how exactly we expand this T of x star. Here we introduce a new set which is denoted by T of x star mu. And the only difference of T of x star mu compared to T of x star is that we add one condition here, and mu j greater than 0 when we treat the inequality constraints. So when we add these active inequality constraints into the definition, so if we just remove this part here, we obtain exactly the definition of T of x star. But let's see what this condition that we add here is about. we add this equation here in the definition of T of x star mu only if, first, the constraint is active, and second, the corresponding Karush-Kuhn-Tucker multiplier is not zero, so it must be positive, okay? So remember, what was the role of the Karush-Kuhn-Tucker multiplier? The Karush-Kuhn-Tucker multiplier must be zero whenever the constraint is not active, right? So if the constraint is not active, then Gj of x star is not equal to zero, and by complementary slackness, mu j must be equal to zero. So, and then because mu j is equal to zero, we essentially eliminate the non-active constraints from the Lagrangian, and we focus only on the active constraints. But sometimes the constraint may be active, which means that Gj of x star is already zero, but still the Karush-Kuhn-Tucker multiplier mu j could also be zero, right? So the complementary slackness condition requires that the product of these two is zero, but both of them could be actually zeros, right? So in this case, we essentially eliminate this active constraint from the Lagrangian, even though it's active, right? So it looks like this constraint is not important for the local optimality properties, okay? Therefore, if mu j is zero, then we wouldn't include the corresponding constraint in the definition of the tangent space. We only look at active constraints that have a positive Karush-Kuhn-Tucker multiplier here. As a result, because potentially we can drop some of the equations from this set, from the set that we had in T of x star, so if some of the Karush-Kuhn-Tucker multipliers were zeros for active constraints, then this would mean that we drop some of these equations here, and then when we drop the constraints in the definition of some region, then obviously this region expands, right? So the region becomes bigger, so therefore we have T of x star is a subset of T of x star mu. If all the Karush-Kuhn-Tucker multipliers are positive for active constraints, then these two sets would coincide. But in case when there are active constraints for which the KKT multiplier is equal to zero, the T of x star set will be strictly contained in T of x star mu. All right, so and we need to require the positive sign for this product over the set T of x star mu, not just over T of x star for sufficient conditions. Now we can formulate the second order sufficient conditions for this case. If x star is a regular point satisfying the KKT conditions and the second order necessary conditions with some lambda in Rm and then non-negative mu in Rp, and in addition to that, for any non-zero y from T of x star mu, this inequality holds, so we have strictly greater than zero sign here, then we can claim that x star is a strict local minimizer for our problem.